Hello, everybody. My name is Lars Lindner, and I'm a German guy living in Mexico, Mexicali. That's the reason I put on this shirt, Mexican shirt. It's called Guayabera in Spanish. And I am living here in Mexicali. It's on the border to the United States, on the north of Mexico, and I like the country and the people, and they're very nice. And our research team and me, we are researching in optoelectronics and automated measurement. And since my PhD work, I am working with a novel laser scanning system, which I developed. And I want to talk about this a little bit later. And today I want to present you a new approach, what we are using right now to amplify the received laser signal using a transimpedance amplifier. And the reason for this is to extend the scanning range. So this presentation is about the proposal and the experimentation results, what we received, my student and me, and the steps taken for the detection of presence and distance of scanning objects using a transimpedance amplifier with a low power laser scanning system. Like everybody knows, lasers are widely used in industrial and research, and for example robotics, to mapping and to steer robots in unknown environments, and measuring construction, measurement and surveying of environmental objects, any objects where you need determining 3D coordinates of surfaces, you can use laser scanning system. And mostly we can say that the big advantage that we can offer of our laser scanner is that it's a fast single sensor and very reliable system to detect 3D coordinates, and also a low-cost system. Here you can see a small picture of our laser scanner. It's the prototype number 3, which I developed since my PhD here at the university. It contains mainly of 2 main parts: the laser positioner on this part, the main arm in the middle, and on the other part is the scanning aperture, whereby the laser positioner redirects a green laser light using a 45-degree cut mirror. It redirects it in front to the laser scanner. It got reflected from the object, which is here, got received by the scanning aperture. So by forming this triangle, measuring these 2 angles, the distance is known by the structure. You can determine exactly the 3D point of this reflected laser point. This principle we are calling dynamic triangulation, because we are moving dynamically the laser positioner and dynamically scanning the reflected laser point using the scanning aperture. Also, our 3D scanner can be moved in 3 dimensions by using a third motor on this side, which in fact are right now DC motors compared to the old prototype number 2, which were only stepping motors. And the advantage of using DC motors that you can receive a continuous scanning field of view. Here you see the processing circuits of the old prototype, which only used photodiodes and a comparator to detect the received signal by using an impulse. Our new approach is to detect the whole signal by reading the whole energy over time, not only pulse when it's presented, rather than measuring the received signal, and using this signal to detect the rotations and positions of the DC motor, what we're using to position our laser in the field of view. So we have here a little system overview of our scanning aperture. which consists the laser got reflected, the laser signal got processed by optical sensors. They convert the optical signal to electrical signals, which thereby gets amplified, and later data processed. So the data must be read and processed using analog digital converters, of course, and an algorithm which we also invented is used to calculate the angles of the reflected laser beam. Here we can see our proposed photodiode, which we are using right now to do experimental. It's the photodiode BPW21R, which has a high sensibility to visible light, a higher middle sensitive angle, and also a higher area of sensitivity. Here you can see the responsive curve of this photodiode. Photodiodes normally are operated in two different modes. One is called the photoconductive and the other one is the photovoltaic mode. The two schematics are shown here in this figure. The transimpedance amplifier can be modeled by using the following block diagram shown here in this picture, which is widely used in literature. It's represented by a positive feedback loop or closed loop, which can be modeled using this equation, which also can be simplified using this equation. So here we can see some measurement results of our experiment. The sensor was inside of the scanning aperture. The laser beam positioned on the reflection object. It's a small metallic part, which we used as experimental object. It got reflected and received by our sensor, and we only, on the beginning, measured how many current we received without amplifying it. So we got a small dark current, which is almost 0 microampere. And later, when we positioned the laser, we received a small amount of current, less than 0.05 microamps. Next, we have next experiment using the same sensor and turning on or turning off the lights in our laboratory, because this highly influence the measurement results, because obviously there is some kind of disturbance, light disturbance of our sensor. So we did two different experimentals. And as you can see, we also use two different surfaces, a metallic cylinder and opaque wall. So the metallic cylinder is more reflective than the wall. So that's the reason why we received, after amplifying the signal, more voltage than on the wall in both cases. And you can also see that by increasing the distance, we received voltage after the transimpedance amplifier is less than when you are near. So we can discuss the results of this measurement, that the range of our system can be increased using this transimpedance amplifier, because before, with the old schematics of the comparator, we only received like 30 centimeters of scanning distance. And with this, in the instruction transimpedance amplifier, we received until meters. It's also the least noise in the signal, digital filtering, and there's also an easily measurable between the distance of the object measured. So in future work, we will also research about more creating an algorithm to filter and process the signal in the amplifier to auto-calibrate counts to create your account, brightness of the room, taking the brightness of the room, calibrating the sensor, sensibility, integrating this amplifier to the actual control software of the TES, and set up measurements in synchronization with the movement of the laser positioner and scanning apparatus to map reading coordinates. I thank everybody for your attention, and I stay for questions in my email or in paper. I hope you come from you. Everybody nice, chill, and stay healthy, everybody. Bye.